Hello and welcome to this first in a short series of podcasts on navigation. I'm Aidan Thorn, Marine Robotics Business Development Manager here at Sonardyne, and I'll be your host for today. So why is navigation important? Well, in marine robotic operations, reliable and accurate navigation doesn't just ensure that your vehicle is in the right place, but it also ensures reliable and accurate data collection. And so it's really fundamental to how your marine robot performs. Over this series of podcasts, we're going to be speaking to expert collaborators and clients to discuss what we're doing in subsea navigation. In today's episode, we have a panel of 3 experts pulled together via a great collaboration with McGill University that we've been lucky enough to be part of through our sister company, Voyis. They're all together today at the Voyis facility in Canada. Hi, guys. So without further ado, I'd like to introduce James Forbes, who is Associate Professor and Williams Dawson Scholar at McGill University, as well as Thomas Hitchcox and Ollie Tracey from Sonardyne. Ollie is our Principal Navigation Systems Engineer, and Thomas is a Navigation and Mapping Research Scientist. Thomas, you've had an interesting route into that role via this collaboration between McGill and Voyis. Can you tell us a little bit about that, please?
Yeah, of course. So I came into this role in sort of a roundabout way, as with most things in life. I first joined what was formerly 2G Robotics 5 years ago as part of a collaborative PhD supervised by Professor Forbes. And the focus of my project was on mapping with Voyis's laser scanning products. So along the way, I developed some algorithms for point cloud alignment, and that basically allowed us to perform trajectory correction over time. So the focus of the project was improving both the navigation side and the mapping side using some of Voyis's systems. And Voyis was acquired by Sonardyne, now the Covelli Group, a few years back. And through that connection, I came to work for Sonardyne as a navigation and mapping research scientist.
Great. Well, it's good to have you on board, Thomas. James, can you tell us a little bit about how that collaboration with Voyis and McGill was initiated in the first place?
Yeah, so actually at the time it was 2G Robotics, and they reached out to me. They knew I was working in this space of autonomous systems, of navigation. And in Canada, there's some really great funding programs that allow or enable collaborative research with companies. And so we wrote one of these grants. It was funded, and that led to a really great collaboration with 2G, which is now Voyis. And Thomas was part of that project. There's been some other students part of that project. And we've had a lot of fun, solved some really interesting problems. And it's been a really great experience.
Fantastic. Great. And Ollie, you're the last one on the screen there. You joined Sonardyne last year. Can you tell us what brought you to Sonardyne?
Yeah, so Sonardyne for the last 11 months. Two decades worth of experience sort of in modeling, simulation and algorithms, plus quite a bit of software development over the time, mostly for the defense sector. In that work, I tended to find navigation was the thing that made me really want to get out of bed in the morning. Spent some time as a lead algorithm developer on fiber optic and MEMS systems, and now I'm here as the principal navigation systems engineer at Sonardyne.
Great. Well, thank you all very much for taking the time to come and speak with us today. Appreciate you taking the time out of your busy schedule over there at Voyis, and hopefully we won't take too much of your time. Okay, so this podcast, as I say, is all about navigation. So let's start by looking at what some of the challenges are in navigation. If we start by talking about what these are generally, so in above water, maybe on land or anywhere else, and then look at what the challenges are as we move below the water surface. So James, if we can start with you on that, please.
Yeah, sure. So when I hear the word navigation, what I think of is essentially figuring out where a vehicle is, be it in a drone or a ground vehicle or an underwater vehicle, where that vehicle is either relative to its environment or in some sort of world frame in some sense. And so there's some common challenges amongst all domains. So first of all, rarely do the sensors measure exactly what you're interested in. So for example, an IMU will give you like rate gyro measurement, which is an angular velocity measurement, but often you're interested in attitude. So then you might have a camera, for example. So you need to take the camera data as well as the IMU data, the accelerometer, the rate gyro data, and you want to fuse that together to get an estimate of what you're actually interested in, which is, for example, the position of a robot relative to some feature. And so that's one of the first challenges. You're not directly measuring usually what you're actually interested in. Another challenge that's common amongst all these domains is that the sensor data is noisy and biased. The biases in particular can be pretty tricky, especially when you're trying to do long duration sorties. And so these are kind of the common things that we have to overcome in all domains, actually.
Fantastic. Ollie and Thomas, in terms of the underwater domain, what are the specific challenges there? Ollie?
I would guess the biggest one is the absence of GPS. Like subsea, an absolute position is not there really. We can provide systems that can get it there, but it's not as abundant as what it is on the surface. Also, subsea vision is obscured due to the water and things like that.
Yeah. During my my work with Voyis, working with these laser scanning and camera systems, and other challenges, most of the environments you're navigating around are frankly pretty boring, pretty flat, featureless, dark as well, which leads to some illumination challenges. So using sort of front-end optical systems has its own host of challenges, just navigating that feature-sparse environment.
Great. And James, you talked a little bit about the wider world, navigating anywhere. Is there anything that we can learn in the subsea environment from people that are operating in the other parts of the world?
Yeah, definitely. There's been a lot of work in aerial and ground robotics. We are all hearing about self-driving cars, and there's definitely lessons to be learned when we transition to subsea. Honestly, often my students and I, one of the first things we do is just see if we can almost plug and play what's been done in aerial robotics or in ground robotics into the underwater world. However, as both Ollie and Thomas mentioned, it usually is not plug and play. There's usually some gotchas, let's call them, when we transition to the underwater world. But definitely, yeah, like we try not to reinvent the wheel unless we really have to. So we definitely try to, stand on the shoulders of giants, as the saying goes, and leverage what's been done in aerial or terrestrial robotics. And then because of the challenges of subsea, often we have to develop some very tailored and nuanced solutions. But that's just because of the environment we work in. So yeah, we definitely try to learn as much as we can from the existing literature.
Right. And so from a Sonardyne perspective, our solution for navigation is our SPRINT-Nav family of products. Ollie, can you tell us what a SPRINT-Nav is, please?
How it works, it's a high-end IMU. It's a DVL and pressure sensor or depth sensor. That combination subsea is awesome. Like that can really get you far. It bounds your position, positional drift from your IMU. So the IMU and the DVL work really well together. Its SPRINT-Nav is a tightly coupled system between its IMU and its DVL, so it's able to work off beams, which means it can go more places than a standard loosely coupled system. It's also got great integration with LBL, USBL. It can take latent USBL measurements. And another key point of the system is it works with our Janus post-processing software. So we're able to smooth a solution over a large dropout of absolute positioning somewhere. It's a great system.
Great. And Ollie's mentioned a number of things there, Janus, LBL, USBL. Just for anyone that's new to any of this, there will be some show notes in this underneath this episode. So yeah, we'll be able to point you at pointers for for any of those things as well afterwards. So yeah, do check the show notes out if you want to dig a little bit deeper on it, any of the things that Ollie's mentioned there. Thomas, you obviously used the SPRINT-Nav in your research project. Tell us a little bit about how you've used the SPRINT-Nav and how it supported your work.
Yeah, gladly. So again, working with these, optical sensors at Voyis, we need a navigation solution to build up our maps over time, our laser submaps. And for my work, that navigation solution was supplied by a SPRINT-Nav. So we use this for some development work here in Canada, going on deployments with Voyis. And I've also used that navigator for some more interesting field trials that we've come across over the last 4 years, including the Wreck of the Endurance last year was a SPRINT-Nav system, and that was a real treat to work on. So having a very reliable navigator is important, especially when you're working with point clouds, because you need to be able to resolve all of the sort of fine high resolution features in your laser scan, and that's, I think, where the SPRINT-Nav really shines.
Great. Let's expand on that a little bit now, actually, because as we said in the introduction, that navigation isn't just about getting from A to B. It's also about that data that the vehicle is gathering. So, James, Thomas, I know we've spoken before about balancing relative mapping requirements with user needs for absolute accuracy, and the difference between relative and worldview in navigation and data collection. Talk to us about your work in that area. If you can start with you, James.
Yeah, sure. So maybe I'll start off very high level. When I think of an autonomous system, there's really 3 problems that need to be solved robustly and reliably. So there is the navigation solution, the path planning solution, and actually the control solution. And they have to work synergetically together. Navigation is all about basically figuring out, well, where is the robot in either the world or relative to some features. And that's what you're getting at, Aidan, this idea of where's the robot relative to something of interest, be it infrastructure or a shipwreck, versus where is it in the world and globally in some sense. Then the path planning problem is, okay, we know the robot is here, or we have a very good estimate of where it is. What path do we actually follow to, for example, inspect this piece of infrastructure? And the control problem is, well, what actual kind of thruster inputs do you give the vehicle? And that could be done by a human operator, or it could be done fully autonomously. And so that's the whole, I would call, autonomy loop, if you will, the navigation problem, the planning problem, and then the control problem. And then as we just alluded to now, when we talk about navigation, we can talk about, well, where is the vehicle in some sort of global frame? And GPS will give you that, essentially. But as Ollie mentioned earlier, in subsea, often what's actually important is the relative navigation solution. So if you're looking at some sort of infrastructure, you're trying to inspect that, what really matters the most is where certain features are, whether it be, a piece of concrete or, some part of a wind turbine pile, where is that relative to another feature? And so that's where a lot of the work that, for example, Thomas did with Voyis really focused is on these so-called relative navigation solutions. And what's really important there is what is so-called a consistent solution, something that's both accurate and trustworthy in some sense. And so we've done a lot of work with Voyis on that.
Okay, that's really interesting. Ollie, did you want to tell us about some of the algorithms that are used to do this?
Yeah, sure. One of the key algorithms is something called SLAM. That's simultaneous localization and mapping. Within that, there's a few different varieties of navigation you can do. You can either do just purely navigation, which is purely mapping, or a bit of both. And that's one of the key ones we utilize.
Fantastic. Thomas, I know we've sat in a room together in the past and you've put slides and slides of equations on the screen and, the sort of thing that many of us mere mortals, don't really understand, but are very glad that there are people like you that do and can make things work really well. Can you tell us about how the maths that you do and some of the batching solutions that you're working on create even better navigation solutions?
Yeah, gladly. So the tool that's been most often used in the subsea industry for a long time is the Kalman filter, or different flavors of filtering. And that's a navigation solution that processes data sequentially. So one sensor measurement at a time, so to speak. And it gives you a real-time solution that you can then use for control, sort of part of that autonomy loop that Professor Forbes was alluding to. So one of the approaches that we've taken as part of our research is a different sort of navigation solution called a batch problem, where you're essentially looking at many measurements over time, and you're fusing them together as part of the same optimization problem. And that's going to help improve navigation robustness, for instance, to outliers. And it's also going to provide you with a smooth navigation solution. So potentially a more smooth real-time estimate.
Thanks for that, Thomas. Anything you want to add on that, James?
Yeah, just to build off on what Thomas just mentioned. Yeah, we tend to solve these navigation problems in a batch framework, and really that means we're solving a large optimization problem. And some of the more mathematical stuff also involves a robust, reliable optimizer. And so we've spent a lot of work on that within our research team. Also something that I would say is quite popular in aerial and ground vehicle robotics is how do you actually represent the navigation state of the vehicle. So we use this, it's somewhat of a mathematical tool. It's called matrix Lie groups. But at the end of the day, we use that tool to represent the state because it's a very, I'm going to say the word efficient. I'm also going to say reliable. I'm also going to say the word unique attitude representation that fits really well with the way we solve these batch optimization problems. So there's really some synergy on how do we represent the vehicle navigation state, as well as how do we solve the optimization problem. And we spend a fair bit of time making sure that synergy's there.
James, great. Thanks for the explanation. And Thomas, you obviously working out of Voyis at the time when you were doing your research program. Tell us a little bit about how you were using that data.
Yeah, sure thing. So so far we've kind of been talking about optimization and solvers, and that's sort of what we call the back end of this SLAM problem, and that's sort of all the machinery that we use to optimize the problem. But to feed information into that, we have something called the front end, which sort of deals with all of the messy sort of world-facing sensors like cameras and scanners and even DVLs IMUs. So yeah, Voyis, and fundamentally an imaging company, color cameras and laser scanners. I did a lot of work during my PhD with the laser scanner in particular, and so I developed a suite of algorithms. How do we process that data reliably? How do we extract features and key points from that data? A lot of the techniques I used came from aerial and terrain applications, because often when you go down to image something, you have a shipwreck or a piece of infrastructure or something interesting and sort of textured, where you can really apply some of those existing tools. But I also had situations where we were dealing with sort of feature poor areas, so flat seabed, for instance. And the challenge was, how do you use flat seabed to help you navigate? Because the end result of all this sort of front-end work is something called a loop closure measurement. So you can think of if you have a long sortie and your vehicle comes back and is able to recognize that it's revisiting the same place. Again, that happens through the front end. You're basically able to bound the drift that you've accumulated throughout that loop. So it's a way to provide a self-consistent navigation solution without relying on any external sensor like GPS or LBL.
Great, thank you. Ollie, I see you're nodding your head along there as both James and Thomas speak. Tell us how collaboration with research organizations like the guys at McGill is useful to our navigation solutions.
Well, it provides us a great opportunity to come to them with problems. Like if we've got a problem that we can't do ourselves or don't have enough manpower to do it ourselves, we can take it to them they can de-risk large proportions of it with all their wealth of experience, pull in different aspects from different domains. They've got great contacts, and it gets that starter for tech. We don't have to. It's not just a complete blank sheet of paper. They come with us with a prototype or something like that. So we're up and running, kind of thing. So it's great.
Thanks very much, everybody, for a really interesting conversation. This has got me pretty excited about the collaboration that's been enabled by this relationship between Voyis and McGill. You're obviously all there together at Voyis today. So can you tell me a little bit about any future plans, any future collaborations? Maybe James, start.
Yeah, I'd be happy to. So as I mentioned earlier on in the talk, the very first interaction we had with Voyis was through a grant where the Canadian government can facilitate a collaboration. That project went extremely well, so well that we are now doing an extension, essentially another collaborative grant. That's facilitated by NSERC and MITAX, and I'd like to thank both NSERC and MITAX for that support, as well as Voyis, of course. And so in this upcoming grant, because Voyis, which is our primary partner, they make laser scanners and subsea cameras. We are focusing on how do we leverage those wonderful pieces of hardware to enhance the navigation solution. So going forward for the next roughly 2 years, we're really focused on monocular cameras, stereo cameras, taking that data, fusing it with sonar data, the SPRINT-Nav data, other sensor modalities to essentially realize just much more reliable, robust navigation solutions that in particular leverage the Voyis sensor suite.
Fantastic. Anything to add from your side, Thomas or Ollie?
Just in regards to future or upcoming projects?
Yeah, future plans, future collaboration.
Yeah, I can tell you we're keen to sort of explore these batch formulations as a supplement to the existing nav solution, and there's a few sort of side project ideas that we'd like to take back to the McGill team to sort of prototype and maybe look to incorporate some of those sometime next year.
Great, thank you very much. Ollie, any final thoughts from you?
Yeah, like this is a great setup. Like it's a great relationship going forwards. It's exciting, this link back to universities and putting in cutting edge research into our product, and I can't wait. I really can't. It's such an exciting part and transition for Sonardyne going forwards.
Yeah, and from my perspective, like not only do I get really excited about actually getting access to real problems and helping solve these real problems, the students are incredibly excited about this too. Like the students don't necessarily want to sit, in the ivory tower and just do maths all day, right? Like they get excited about real problems and how they can solve these real world problems. So I agree with Ollie, like, in the past, over the last 4 years with Voyis, and we had some really great projects to work on, solve some real problems. And I'm just looking forward more to getting exposed to more problems, helping solve those problems with both Voyis and Sonardyne. So yeah, it's just as Ollie said, it's just an amazing opportunity really to really have an impact. So that's really exciting.
Fantastic. Yeah, I think the best collaboration, the best research, the best innovation always comes out of industry working closely with academia and research organizations. So I think this is a really strong example of that already. And, we've seen people like Thomas that have come through that academic PhD route and ended up in a good, solid career with Sonardyne now. It's good to see things like that happening and the links between the academic organizations and the industrial organizations really sort of paying dividends. So great. I think that really brings us to the end of what we had to talk about today. just want to say a big thank you to yourself, James, to Thomas, and to Ollie for taking part in this conversation today. It's been really great talking to you. I want to wish you all the best for the rest of your time together over there in Canada. Please do say hello to the guys at Voyis for us and say a massive thank you to them, not only for hosting you guys today and giving us the space and the time to do this, but also for introducing us to this fantastic collaboration that we've got going with yourself, James, at McGill University, and all of the other students that we've got working on things and had working on things as well. As I say, I'm really excited to see where this goes next, and maybe we can follow up with another one of these at some point in the future. That would be really nice to see. To the audience, I'd like to thank you for watching. Do check out the episode show notes. I mentioned earlier that there will be a bunch of notes in there where we will be able to link to various things related to this blog. Some of the stuff that Ollie mentioned earlier can be in there. And we will also put links up to some of the published work that's already been done in this field, some of the stuff that Thomas and James have been working on. That's it for this one. Our next episode will be recorded in a few weeks' time during Oceanology International. If you're at that show, do drop by the Sonardyne stand and say hello. But until then, don't forget to hit subscribe and you'll get notified of when the next episode is ready. Thank you very much.